Welcome to the second lesson of the set theory part of Math 1. In this part we're going to talk about some more operations on set, and we're going to do a little bit about counting principles. First operation we're going to look at is the union operation. So if we have two sets, A and B, then the union, denoted with this symbol here, is A united with B, stands for all the elements where the elements can come from A or they can come from B. So it's the collection of all possible elements which are either in A or in B. So for instance, if I would make a set A containing 1, 3, 5, 7, and I have a set B containing 1, 8, 12, and let's say the universe would be the natural numbers again, then the union of the two sets would be 1, 3, 5, 7, and then filled up with all elements of set B, so 1, 8, 12. Well, as we've seen in the previous lesson, that 1 is already there and we don't have doubles in a set, so the union consists of the elements 1, 3, 5, 7, 8 and 12. If we would do that in a Venn diagram, and then if this is set A and this is set B, then the union is this complete area, so all elements which are in A or in B, and the doubles are in this part, they don't count twice. Another operation we can talk about is the intersection, given with the symbol A intersected with B. Okay, so if we look at the previous sets again, then we had a set A containing 1, 3, 5, 7, and we had a set B containing 1, 8, 12. Then if we would combine these in one Venn diagram, then we would get this drawing. So we have here set A with 3, 5, 7, and I'll put the 1 here because that one overlaps with B. So 1, 8, 12 is B. So this one here is B. Then the intersection are all the elements which are in this part. So A intersected with B. So in this situation, A intersected with B would only be the element 1. Yeah, because that's the only one which is in both sets. In a formula, it would look like A intersected with B would be all the elements X, and with the condition X is an element of A and X is an element of B. So it's an and a union gives me an or. Let's have a look at some of the properties of this union and intersection. Well, one of the most obvious properties, of course, that if we have two sets, let's say this is our universe, we have a set A and we have a set B, then the union is of course all the elements in A as well as in B. Then you can see that A is part of this complete set. So A is a subset of A united with B, and equally B is a subset of the union. Also, if we look at the intersection, then we can draw a similar conclusion. So if this is A and I have B, and I will just leave out the universe for now, as you see how bad I am in drawing rectangles, then the intersection of A and B would be this spot here. And of course, this part is a subset of A as well as a subset of B. Another property we can look at is this one. If we look at A being a subset of B, what can we tell? So if A is a subset of B, this is A, then we know that B is something around it, B. And now we can say A is inside B. If we then look at the union of these two, then of course the union is the larger one. So the union means that would be the biggest subset, B. So A being a subset of B is equivalent with the union of the two is equal to B. And also if we look at the intersection of the two, so let's make it another color, the intersection of A and B, that is this part. So the intersection of A and B is A. And so if A is a subset of B, then we know that the union is B, and we know that the intersection is A. But we can also work the other way around. So if we know that A united with B is A, so we start on the right. So then we definitely know that A united with B, the intersection of the two, is A. So that means that this part is contained inside B. So definitely I have to draw B around A because the intersection is the smallest one. Okay, if we look at this picture, then we can conclude, if we go to the left, that the union of the two is the largest one. And of course we can conclude that A is a subset of B. So that means that the relations are logical equivalent. So we can reason from left to right, but also from right to left. If we look at some other operations on set, then a nice one is the relative difference. So if we have a set A, and I will not draw the universe anymore because of my poor rectangle drawing capacity. So if this is A, and I have another set B, then the relative difference of the two are all those elements which are in A, but not in B. So it's the part of A which is not in B. So in fact it is set A without the intersection. And so A without the difference operator. So this would be equivalent with the set A without the intersection. And so that's exactly the same thing. If we would look at the number of elements, so if we look at some counting principles, then the amount of elements in this difference are of course the number of elements. We denote this with this n, the number of elements minus the number of elements in the intersection. Okay, another operation we can look at is the absolute difference, the complement. And now I have to draw the universe again because he is part of this definition. So if we look at this universe, and I have a set A inside this universe, then the complement of this set A, AC, are all the elements inside the universe. So if we read the definition, all the X inside of the universe, but outside of A. So that's the red part. And if we look at the number of elements, so A complement number, the number of elements in this one is of course the number of elements in the universe minus the number of elements in the set A. So that's quite straightforward. The last operation I'd like to look at for sets in this video is the symmetric difference. And the symmetric difference is denoted with this strange symbol, this plus with a circle in there. And the symmetric difference, if we make a Venn diagram, then we have a set A then we have a set B. Then the symmetric difference is A without B, so that would be these elements, A without B, this part, united with B without A, so that would be these elements, so this part. And so the symmetric difference, you can compare it with an exclusive OR. I don't know whether you watched the video about logic already, but the exclusive OR is a similar thing as a symmetric difference in set theory. So it are elements inside A but not in B, united with the elements in B which are not in A. So basically it's the union without the intersection. So the union of the two without the intersection. Okay, before we continue counting the elements in sets and operations on them, let's first look at some simple counting principles. And the most simple rule we can have in a counting principle is called the sum rule. And that applies that if you have several actions to take, and for instance you can do one action in 7 different ways and another action in 5 different ways, and you have to do only one of the 2 actions and you can make a choice, then in total you have 12 choices. So let's say if we have a choice of going to school by car, that's one option, or by helicopter, or by bike, so we have 3 possible actions to take. But we could also say, I don't want to go to school at all, I want to stay at home and then I stay in bed all day, or I'll bake myself a cake. Those are 5 actions we can do. So we can go to school by helicopter, or by car, or by bike, or we can stay in bed, or we can bake a cake. We have to choose from one of those options, then we have 5 choices. And that's in fact just the sum rule. So if you have a choice of doing 2 actions, and you have one possibility of doing the first action in A ways and the other action in B ways, then the total choices you have are A plus B. That's the sum rule. Another simple principle is called the product rule. And now we're talking about independent actions we take in a different time span, we could say. So let's say I'm at home here and I want to go to school. And I can go to school by helicopter, or I can go to school with the bike, or I can go to school with a car, and then I am at school. So I have arrived at the same school. But then when we are at school, we could go from this school, and so now we're here at school. We could go to our classroom by taking the stairs, or we could go to our classroom by taking the elevator. So this is our classroom. Then in how many ways can I go from home to my classroom? Okay, then first I have 3 choices, but when I'm here, then again I have 2 choices. So you can combine these operations by drawing this sort of a graph, which we'll see in MATH1 by the way. And from here we have 2 choices, 2 choices, and 2 choices to arrive in my class. So in total I have 1, 2, 3, 4, 5, 6 different paths to go from home to my classroom. And this is in fact the product rule. So that means that for the first choice I had 3, and then I multiply it with when I am in the second stage here, with for every stage I have again 2 choices. So the product rule means that when I have A ways to perform action A, the first step, and if I have B ways to perform the second step, then in total I have 3 times 2, A times B possibility, product rules. In the next video we're going to look at some more counting principles on sets.